Today we're talking about exponential transformations. And before you watch this video, please make sure that you know how to graph a basic exponential equation. Any addition, subtraction, or even multiplication performed on functions has an effect on their graphs. And those effects are called transformations. There are many different types of transformations that can happen. Transformation is a general term that applies to many different types of changes in a graph. But today we're going to explore and learn exactly what happens or what transformations take place for the addition and subtraction operations. We're going to start with something called a parent function. A parent function can be any type of graph. The definition of parent function, or the kind of general idea of a parent function, is that it's a beginning graph or starting graph before any transformations have taken place. One of the easiest graphs to use when talking about transformations is the absolute value of x. So that's the graph I've started with today. Notice that it has a very distinctive V shape, a vertex at the origin. The right half of the graph has a slope of 1, and the left half of the graph has a slope of -1. Let's take a look at the graph of f of x plus 3 then. This is what it looks like in function notation. If I write it in terms of the absolute value of x, it would look like the absolute value of x, and then plus 3 would come after the entire function or outside the absolute value brackets. So we're going to call this adding outside the function. And of course, if I didn't have the graph already drawn for you and you need to draw the graph, we could start plotting points. We could start putting different values in for x, take the absolute value of those numbers, and then add 3. So like if I put in a -2, absolute value of -2 is 2, plus 3 is 5, so I would have the point -2, 5. Again, you can just start plotting points and get a really good indicator of where your graph is supposed to be. Once the graph is drawn, you can compare the parent function to the new transformed function. And notice that it has exactly the same V shape, still with a slope of +1 on the right and with a slope of -1 on the left. The only difference is that the entire graph has been shifted up 3 units. What if we subtract 3 instead of add 3? In this case, again, looking from our parent function to our new transformed function, exactly the same shape and direction, but this time our graph has been shifted down 3 units. So what's happening when we add or subtract outside the function? Well, when we add outside the function, the entire graph, every point on that graph, shifts up that many units. And if you're subtracting, the graph shifts down. That way, if you see transformations in function notation, you can tell really quickly that the ones on the left are going to be shifting up and the ones on the right are going to be shifting down. And that can help you draw transformations quickly and easily. So let's take a look at what happens in an exponential function. We're going to start with the parent function y equals 3 times 2 to the x power, where 3 of course is our starting value, or y-intercept in this case, and 2 is our rate, so our y values keep getting multiplied by 2 again and again. So in this graph we go from 3, then to 6, then to 12, then to 24, and so on. So then, what if we want to add 4 at the end of the function or outside the function? Well, according to what we just went through, our entire graph would shift up 4 units. And it's kind of hard to tell sometimes Over on the left-hand side of the graph, it's a little easier to see that we've shifted up 4 units. But on the right half of the graph, it's not as easy to tell. So sometimes you have to go point by point to tell that we've actually shifted up 4 units. Like the y-intercept went from 3 to 7. The next point over on the grid that we can tell was here at 1, 6, and that point went up to 110. The point that was at 212 went up to 216, and so on. So even though it looks like those graphs are going to get really close together, it still is a situation where every point has been shifted straight up 4 units. What if we want to subtract 2 from our function? Well, then of course our graph would be shifting down 2 units. And again, you can look point by point. 3 shifted down to 1, 6 shifted down to 4, 12 shifted down to 10, and so on. One item that might help you in graphing transformations is, of course, a table. Like I said, plotting points is an important part of being able to graph, and tables help us do just that. Remember, you can pick random values for x, substitute them into your equation, and then in cases like this, when you simplify this, make sure that you're using order of operations. 2 to the 0 power comes first, 2 to the 0 power is 1, multiplied by 3 is 3, then subtract 2 and we'd get a y value of 1. That means that 0, 1 is a point on our graph. I can do the same thing with 1, again substituting it into my equation. 2 to the first power is 2, times 3 is 6. That's where our original graph would have stopped. But then we have to do the subtract 2, which gives us a y value of 4. So the 0.14 is on our new transformed graph. We can do that for as many values as we need to get a good look at what our graph is doing. Make sure that you try to plug some negative values in for x so you can see where to put the left-hand side of the graph. Even the asymptote itself can help in your transformations. If we go back to our transformed graphs from just a second ago, notice that in our original parent function, the asymptote was the x-axis, or the line y equals 0. When we added 4, even the asymptote got shifted up 4 units. And same for subtracting 2. Even the asymptote got shifted down 2 units. Now let's look at a different type of transformation that takes place when we add and subtract inside the function. This time in function notation, notice that the plus 3 is inside the parentheses of our function. So we're adding 3 to the x value. If I wrote that in terms of the absolute value of x, plus 3 would be inside the absolute value brackets. Now I know it's hard to kind of see why the new graph is where it is, so let's take the time to plug in some x values. If I put in a 0 for x, I would take 0 plus 3 and take the absolute value of 3. That means the point 0.03 is on our new graph. Notice that our new vertex, or 0, is where x is -3. -3 plus 3 is 0, and the absolute value of 0 is 0. I can keep doing that for as many points as I need to. -5 plus 3 is -2, and the absolute value of -2 is 2. I substituted in a -5 and got a 2 in return. So if you look from the parent function to our new graph, which direction does it look like it shifted? This time it went to the left 3 units. And if I subtract 3 inside the function, take a look from parent function to transformed graph, we actually shifted to the right 3 units. And again, I can verify that that graph is right by plugging in different values for x. So when we're adding and subtracting inside the function, it gets a little tricky this time. If we're adding inside a function, it actually shifts to the left. And if you're subtracting inside a function, it shifts to the right. Almost the opposite of what you would think would happen. So again, if I see transformations in function notation, it's very fast to know which graphs are going to shift left and which graphs are going to shift right. And that can help you, again, graph transformations or this type of transformation quickly and easily. Again, in an exponential function, let's take a look at what happens. We're going to have that same parent function, y equals 3 times 2 to the x. If we're subtracting inside a function, remember that we're only subtracting from the x value. That means that my new exponent would become x minus 4. We're not subtracting from the entire function or y value. We're subtracting 4 just from x. And again, if I plug in different values for x, I'm going to get a whole new look for my graph. And if I try this x value by x value, I get the red graph. And if I look at some of the points on my parent function versus the new graph, notice that it hasn't been shifted up or down at all, and we can tell that mostly from the asymptote itself. But we have shifted to the right 4 units. The old point 0.3 is now at 4.3. The old point 1.6 is now at 5.6, and so on. If I'm adding 5 inside the function, again, when you add inside the function, you're only adding to x, not to the whole function itself. If I were to plug different values in for x and evaluate my function, I would get the blue graph. Really quickly, notice that our old point 0.3 is now at negative 5.3, and our old point 1.6 is now at negative 4.6. So we actually shifted to the left 5 units. Be really careful when you're adding and subtracting from the x value only, because it won't simply add and subtract from the x value. So just to kind of summarize, and we'll go more into detail with this in a later video, but just for really quick and easy purposes, when adding outside the function or at the end of a function, your graph will shift up. When subtracting outside the function or at the end of the function, it shifts down. When adding inside the function or to the x value only, your graph is going to shift to the left. And when subtracting inside the function to the x value only, your graph will shift to the right. Just a quick last note. It is possible to have more than one transformation at a time in a function. If our parent function was y equals negative 2 times 4 to the x power, and we subtract 3 from the x, and then add 6 at the end of the whole function, we're shifting this graph, or every point on that graph, to the right 3 units and up 6 units. Just in case you ever see that happen. Also, the transformation that we've seen today, since it goes up, down, left, or right, but none of these actually went in a diagonal pattern, these transformations are called translations. All right, I think I've taken enough time today. Remember, you can rewind and go back through examples if needed. But for now, I'm going to wish you a great day, and I'll see you next time.